Welcome back, guys and gals. So in this particular problem set, we are going to be working on some kinetics problems. And, when we work with kinetics, one of the things we have to do is we have to understand what a rate law is. And so one of the first things I'm going to do is just make sure that we understand that part, and that way we can move forward. So rate laws are based off the reactants, specifically in the orders of reaction. So this is just a basic generic description of how a rate law is written. And so it's basically proportionality where we're comparing the reactants together. We don't care about the products as they're already produced. All we're concerned about is the rate of reaction with respect to each of the reactants that are involved. Now, each of the reactants are going to react in a specific way, and they're going to change in their rates based off of their identity and their overall orders of reactions. So, a couple parts that we have to focus on is the first part is understanding what the rate is. Rate is change in concentration over change in time. K is a rate constant, and then you have your concentration of your two reactants, and then you have M and N. M and N are the orders of reaction with respect to each reactant, and so the sum of those of M and N actually yields the overall order of the reaction. So what we're going to do in this particular problem set is we're going to focus on the rate law and trying to determine what M and N are, and ultimately the overall order of reaction. So we have a reaction that involves mercury chloride and oxalate ions, and we have some experimental data that was collected below. So one of the things that we have to do is, we can see the problems in A and B where it says determine the order of reaction with respect to each of the reactants. So in order to do this, what we need to do is you can't solve for two variables at once. So what we have to do is we have to find a constant so that way it cancels out while changing the other parts. So if we're looking at HgCl2, for example, what we want to do is come in and find where it changes. So here in experiment 2 and 3, it changes. Now, for the oxalate ion, we don't want that to change, because if it changes, well, then now we have another variable. So looking at experiment 2 and 3, they remain the same, which is what we want. And so what I do is I set up a rate law as a ratio. So I want big over small because I don't want fractions in the end. You can work with a fraction, but it's better to work with a whole number. So I'm going to have 2 over 3. So we're going to rate 2. So we set this equal to 7.1 times 10 to the minus 5 divided by 3.5 times 10 to the minus 5. So what I'm going to do is just write the rate law out, and I'm going to put the rate laws for each experiment on top of each other. So we have K over K, and then we have the concentration of, now this is going to be the mercury chloride because it's first. And then we have the other component here. Now, what we see is there's two parts that can cancel. K is going to cancel out, and then this is going to cancel. So what we're left with is just dividing out the rate. So 7.1 times 10 to the minus 5 divided by 3.5 times to the minus 5 gives me, or divided by, here, let's see, 2. I'm just going to round it to 2. Now 0.105 divided by 0.052 is also 2 to the m power. Now the question is, what is this equal to? So what to the power m is going to give you equal to 2. So 2 to what power? So if I do 2 to the first power, I'm going to end up with 2. So that's what we need. That's what it solves for. So m is equal to 1 here. So what that means is that mercury chloride is first order with this particular reaction. Now we'll do the same thing for the oxalate ion, and so again we need to find 2, keep the other one constant. So what I'm looking at here is it changes there, and this stays the same, so that's perfect. So here we're going to have 2 over 1, because again I want the bigger over small, so we don't want to have any kind of fractions. I don't like fractions. A little easier to deal with whole numbers. You can work with fractions if you want, but not me. 0.105. We know what m is, but it don't matter here because this is going to cancel, this is going to cancel, and you end up with 0.3 to n divided by 0.15 to n. So again, we're going to take this, we're going to divide out 7.1 divided by 1.8, and that gives me 3.9. So that's going to be 4. Roughly, that's going to be 2 to the n power. So 2 to the second power gives me 4. So 2 squared is 4. So n equals 2. So what we've just done here is we've calculated and determined what m is and what n is. Now, the next thing we're going to do in part C is what is the rate law for this reaction? So we're just going to take the information that we're given. So rate is equal to K. We calculated the m. So m is to the first order. Now you don't have to write 1 up there. I'm just writing it so we can see it. It's not necessary to write it. And then this is going to be to the second power. Now the last question that we have here, we are going to answer E, but for right now, the last question, what is the overall order? So the overall order is the sum of the exponents. So overall is equal to 1 plus 2, which gives me 3. So that means that this overall reaction is third order. Now, the last question here is involving the rate constant K. So what we want to do is solve for K. Now, K is a constant, so you could realistically use any of the experiments and you'd calculate the same K or relatively close to the same value. So we can pick any experiment, so I'm just going to pick experiment 1. And what we do is just take the information from experiment 1 and we plug it into the rate law and we just rearrange and solve for K. So you have 1.8 times 10 to the minus 5, and units are important here, is equal to K times 0.105 times the other one, which is 0.15. Now, if you notice, I'm keeping the unit molar, capital M there, because K units are dependent on the overall order. So you have to show your units throughout this calculation. So we're just going to divide out those together here. All right, so you have 1.8 times 10 to the negative 5 molar per second divided by 0.105 m. And then you have 0.15 molar squared. All right, now what's going to happen here is the molar are going to cancel out there. You are going to have molar squared, so be really careful when you plug this in your calculator. You could do this individually and just plug it back in together. I'm just going to make sure I use parentheses here. So I'm going to make sure your bottom has parentheses around it. Now what I end up with here is 0.00762. The units for molar, you end up with molar to the minus 2 times seconds to the minus 1 because both are in the denominator. So you have reciprocal seconds, and this would be your rate constant for that reaction. So what do we learn from this? What we understand and what we have to understand is that when you're solving for the individual orders of reactions, you need to make sure that you're very specific about keeping one constant and altering the other. You don't want to have both of them changing. That's not going to work. Once you solve for your orders of reaction, you then can write your rate law and figure out the overall order of the reaction. and you can utilize that information to then determine the rate constant for that reaction.